so this is a 3-part question, but it kind of helps you through the steps. So they give us that it's this function, this parabola, submerged under some kind of fluid, I guess. This is actually just going to be water, I believe. Yeah, this is underwater. Okay, so this function here, so our normal u, okay, and this is bounded by y equals 1. So here's 1, here's -1, and here's 1. Okay, so here's the line whoa. Okay, hold on. Let me try to actually go through 1. So there we go. So this is our y equals 1. Okay. And then yeah, so it's bounded by these two curves, and this is y equals x squared, obviously. So this is the area that we're looking at, basically. Okay, so for the first part, it says prove that, let's see, what is it? So A is asking us to show that the width of R, so they're just calling this region R, so that the width of it, the horizontal distance, is f of y equals 2 radical y. So let's prove that first. So basically what we have here is, like, if we pick any value of, so here's our x and here's our y. So let's say we pick somewhere here. Alright, so this is a random, like, x value. And whatever it's going to be, however tall it's going to be, or its value, is going to be x squared, right? So this is our y value here. This distance right there. And then this, the depth, is actually going to be 1 minus y, right? So this is 1 minus y. So we have that so far. Okay, and then, so we know that this parabolic curve is going to be y equals x squared. So if we want to find what this x value is in terms of y, then we just get x by itself. So x equals square root of y, plus or minus, right? So this value here is actually going to be the positive one. So let's see. So this value is positive square root of y, and then right across from it at the same height, that should correspond to a value of negative square root of y. Okay? So our horizontal distance, as we can see here, if you just translate it to the width on the x-axis, that would be positive square root of y, so positive square root of y, minus the negative part, minus negative square root of y, which we can see is 2 times square root of y. Okay, so that gives us our width. This is like our horizontal width. Alright, so that was the first part of A. And then it also says that find that a horizontal, the fluid force on the side of a horizontal strip of thickness. So again, like I was showing in the concepts video, we're going to make like a little strip or a rectangle. Okay, so it's like that. Sorry, it's getting kind of cluttered in the picture here. But so this is like height y, or depth y. I like to call it depth, more or less, because then I know that I'm measuring it from the top, like the water line. And then remember the little width on the side here? Again, sorry this is so cramped and cluttered, but this is like our delta y. Okay, this is our change in depth, according to this rectangular strip. And then we also have that this is our f of y. That's our horizontal, right? So here's our rectangle again. Whoa, that wasn't connected. But here's our f of y. And then up here above the rectangle, that's a depth of y. Okay, that's what they told us. And then the little width of the rectangle is going to be delta y. Okay. So alright, let's see. So what we actually have for the fluid force on the side of a horizontal strip of thickness is going to be, well, here's our force. So that's the fancy P and the G. And then we have, let's see, so we're going to have our f of y, which is 2 square root of y. And then remember how we found the depth to actually be 1 minus y value? So this is going to be our depth, all right? So 1 minus y. So actually, correction, I'm sorry. This isn't going to be y, it's going to be 1 minus y, because that's our depth, all right? So because we're measuring from 1 to down to the curve, okay? And then our delta y just takes care of like all the changes that we have going on within this rectangle on the sides, okay? So that was it for part A. That was kind of chaotic, I'm sorry. But now let's move on to part B. Okay, so part B, it says to write a Riemann sum, so that sounds familiar, adding up rectangles, that approximates the fluid force F on a side of R and use it to explain Y. And this is the final, this is what we're trying to prove, basically. So we have 0 to 1, and then 2, y to the 1/2, 1 minus y, and dy. So here, this is kind of, sort of self-explanatory, but because now we're familiar with the Riemann sums. But let's say we have our curve again, right? And then here's y equals 1, all right? So what we're going to be doing, like I said before, is kind of approximating this with rectangles, all right? So we have multiple rectangles kind of filling up this region R, or this area, right? So we have rectangle. That was actually pretty good. So we have, like, let's say first rectangle, second rectangle, third, and so on, okay? So our total fluid force, fluid total, is going to equal the force felt by one, the first rectangle, plus the force felt by the second one, and so on, right? Until you get to Fn, or whatever, however many rectangles you have, basically. Okay, so as n, remember n in the approximations that we've done before, that equals the number of sub-intervals. So this is going to correspond to the number of rectangles, right? Number of, ooh, that was weird. Okay, hold on. Rectangles. So as n goes to infinity, so this is our explanation part. So as n approaches infinity, so as you have an infinitely small, I guess, infinite number of sub-rectangles here, so as they get thinner and thinner and thinner, and basically your approximation is going to become more and more and more accurate until you approach the actual value of the fluid force on this section of the parabola. So basically, as I was saying, so as n approaches infinity, then our limit is going to approach the actual value of the fluid force. So as we know, as the limit of a Riemann sum, that's going to be, f is going to approach this value. So we're basically just going to get the thing on the top, right? Because integral is when you take an infinite number of subintervals, right, from 0 to 1, because that's where we're going from 0 to 1, of 2 square root of y, 1 minus y, and dy. Okay? Alright, so now moving on to part C. Okay, so for part C, first of all, I just want to write down that the mass density of water is 10 to the third kilograms per meters cubed, and that g, the gravitational constant, is always going to be 9.8 meters per second squared. Okay, so it wants us to evaluate the integral. So we're just going to have, well, yeah, okay. So we'll plug in our 10 to the third, and then we have, and then times our 9.8, and then we have the integral from 0 to 1, and then 2 times square root of y, so that, or that would be y to the 1/2. Ooh, that's a 1. Okay, that turned out weird, hold on. 1/2, that's good. 1 minus y and dy, right? Okay, so now we just evaluate the integral. So we have f equals, this is 196 with 2 zeros, And then we can also bring out the 2, I suppose. So that's a 2 right there. No. Wait, sorry. Hold on. Go back. This 19,600, that accounts for the 2 outside. And then from 0 to 1. And then if we distribute here, we get y to the 1/2 minus y to the 3/2 and dy. Okay? So this is going to be 19,600. And then we have y to the 3/2 with a 2/3 in front to cancel out. And then minus y to the 5/2 with 2/5 in front, evaluated from 0 to 1. Okay? So then I'll go on to the next slide to show the rest of the math. So then we get 19,600, and then 2/3 minus 2/5, and then minus zeros, right? So our actual ending value turns out to be 78,400 over 15, which is about 5,227 newtons. Okay? Alright, so that's approximately the total fluid force found experienced by R. Alright.